Welcome to Marine Gurukul video series. In this video, we shall try and discuss some of the stresses that are experienced by the ship's hull. And these stresses exist on the or act on the ship's hull throughout the ship's life, notwithstanding whether the ship is stationary or moving, or whether the sea conditions are calm or rough. Such stresses which do not depend on whether the ship is moving or not, nor do they depend on the sea condition. Such stresses are referred to as static stresses. Why do we need to learn about these stresses? It is these stresses which will try to deform or break the ship's hull, and therefore there shall be a need to strengthen the ship's hull to withstand such stresses. The ship's basic hull that is required to displace water, thus creating buoyancy to keep it afloat, comprises of the keel plating, the two sides, and the deck. Now, why and how much does this structure has to be strengthened? Do we just put a very thin plate, make an enclosed structure, and would that be able to meet our requirement, or do we need to strengthen it? The ship's hull is to be strengthened to withstand stresses induced by various forces that act on the hull. The hull is subject to various forces which we shall learn during the course of our discussion, and these forces induce stresses in the ship's hull, and the hull has to be strong enough to be able to withstand such stresses. A ship's hull stresses can be categorized into two: static stresses that are caused by forces acting on a stationary ship in calm waters. So static ship, static sea conditions, or the dynamic stresses caused when the sea is choppy or the ship is moving. So basically, when the dynamic stresses, if they exist, they'll coexist with the static stresses. Static stresses will always be present, and in conditions where dynamic stresses also exist, they will be over and above the static stresses, or they'll modify the value of the static stresses. Static stresses that are induced by the forces on the ship, even if the ship is stopped and the sea conditions are calm, these static stresses are longitudinal deformation of the ship, termed as sagging or hogging depending on how the hull deforms, the water pressure is exerted on the immersed part of the ship's hull, localized loading if the loading of the weights is non-uniform, and dry docking stresses, which of course will be conditional, will apply only while the ship goes to dry dock. Let's first learn about the longitudinal deformation. How does the ship float, or why does the ship float? Ship floats because there is an equilibrium between the downward weight of the ship, called as the displacement, and the upward force of buoyancy. When these two forces reach a condition of equilibrium, the vessel floats. Now, needless to say, the buoyancy has to be then equal to the weight of the ship. And what is buoyancy equal to? Buoyancy is equal to the weight of the water displaced by the ship's underwater hull. Thus, when the ship is floating free, ship's total weight, that is her displacement, is equal to the total buoyancy experienced by the ship. However, the total weight that comprises of the weight of the ship, including its hull, equipment, cargo, bunker, water ballast, crew effects, etc., etc., is not necessarily going to be uniformly distributed along the length of the ship. So yes, the ship as one body has a certain weight, but is this weight uniformly distributed all along the length? No, the weight is not going to be uniformly distributed along the length of the vessel. There will be some portions where there will be higher concentration of the load vis-a-vis the other portions. Likewise, Because of the varying form of the underwater hull, the buoyancy contribution from each portion of the ship along its length is not going to be same. In the GA plan, we have seen that the ship's bow has a different structure, that is the forward part. The after part, the structure is different, and there is also a parallel middle body. Now that means the contribution of the water displaced providing the buoyancy to the vessel is going to be more from the parallel middle body compared to the two ends. So, because of this varying form of the ship's underwater hull along the length and the varying draft of the ship, which could be because of the trim, the buoyancy is not going to be uniformly distributed along the ship's length. So we have just said the weights are not going to be uniformly distributed. Likewise, the buoyancy, the total buoyancy is going to be equal to the total weight, no doubt. But is it going to be uniformly distributed? No. So, whereas total weight or the displacement of the vessel is equal to the total buoyancy, the two need to be exactly equal in totality, but are these two going to be exactly equal to each other for different portions of the ship along the length of the vessel? No, they will not be exactly same portion per portion. This discrepancy in these two forces not being equal for each section of the length results into the longitudinal deformation of the ship. There are two types of typical deformations depending on which part bends downwards and which part bends upwards. They are called as hogging and sagging. Let us now discuss the condition referred to as hogging, and of course our discussion is limited to hogging in static conditions called as static hog or static hogging. We know that when the ship is afloat, freely floating, displacement has to be equal to buoyancy. In this diagram on the screen, you can see the ship coming up. It's floating at the water line, which is now shown on the diagram. Now we'll divide this ship into three distinct parts. One forward part, one middle part, and one after part. As you can see now, you have the forward part, middle part, and after part. And of course, the displacement of the ship W will have contributions of the weights from the forward part, from the middle part, and from the after part. And let us say in this case, the weight contribution from the forward part is W1. You can see coming up here on the screen. By the middle part is W2, and by the after part is W3. So we have considered a scenario in which the concentration of the weights on the ship is greater at the ends and lesser in the amidship region. Now this ship would also be experiencing, of course, this total W would be equal to sum total of W1, W2, W3. The ship would be experiencing buoyancy, which will depend on the underwater volume of the ship in each of these portions. So let us say the contribution of buoyancy from each of these portions happens to be, say, B1 in the forward part. That means this underwater volume in the forward part contributes to total buoyancy, and that is B1. And we say in this case, we are assuming that the weight concentration in this portion W1 is greater than the buoyancy contributed by the underwater hull form in this part. So W1 is greater than B1. That means as far as the forward region is concerned, the resultant force between displacement or weight of the ship and the buoyancy is acting downwards. Why? Because W1 is greater than B1. In the middle part or in the midship region, the buoyancy is B2, and here we are assuming that B2 is greater than W2 or W2 is less than B2. Therefore, the midship region is going to experience a resultant of upward force. Why? Because W2 is less than B2. Likewise, in the after part, we are assuming that B3 is less than W3, and therefore there is a downward resultant force in the after part. Of course, the buoyancy also in this case would be sum total of B1, B2 and B3, and W will be equal to B as already said. Now if you see the resultant forces, at the forward end there is a resultant downward force, in the middle part there is a resultant upward force, and in the after part there is a resultant downward force. So if we represent the ship as a beam like this, where the upper part represents the keel, the upper part represents the deck and the lower part represents the keel. So at the forward, in the forward region or at the forward end, I can say there is a resultant downward force acting. In the midship region, I can say there is a resultant upward force acting, and in the after part, I can say there is a resultant downward force acting. Now this set of forces at the ends resultant acting downwards, in the midship region resultant acting upwards, is going to cause this ship's beam to deform. And how would the deformation take place? I'm sure you'll agree with me. The deformation would cause the ends to bend downwards and the midship region to bend upwards, as being shown by the green lines which are coming up as a deformed beam or the deformed hull of the ship. This condition in which the midship region is bent upwards and the ends are bent downwards is what is called as hogging. Needless to say, when the ship is hogged, the draft of the vessel amidships would be less than the mean draft of the ship. The mean of the drafts at the two ends. Why? Because the draft at the two ends has increased because of the downward bending, and therefore their mean shall be greater than the draft that will be read amidships, where the ship has bent upwards. Now, when the ship is hogged, the upper parts of the ship, that is the deck region, you can see the deck region here coming in this diagram, is getting stretched and is under tension, or the upper part is under tensile stress. It experiences tensile stress. Likewise, the keel part or the lower regions of the ship would be experiencing compressive stresses that tends to get compressed. So the lower parts of the ship experience compressive stresses and the upper parts of the ship experience tensile stresses. So therefore, the ship's hull has to be strong enough to withstand such stresses. There is only one portion or one line you can see here where the length of the beam or the ship before bending and after bending, you can see this green line coming up here, where the length of the ship or the beam before bending and after bending remains unchanged. That particular axis is called as the neutral axis. So the hull part along the neutral axis is the only part that is spared of any stresses because of this longitudinal bending. So it is neither under tensile stress nor under the compressive stress. Otherwise, the upper parts experience tensile stress, lower parts experience the compressive stress, and the ship's hull has to be strong enough to be able to withstand these stresses. Having understood the hogging condition, we will now move on to a condition which results into sagging of the vessel. We have the same situation where weight is of course going to be equal to buoyancy. We have the ship with its waterline being shown in the diagram. We divide the ship as earlier in the previous case into three portions: forward, midships and after region. Now only difference now is we have higher concentration of the weights in the midship region and lesser concentration of the weights at the ends. We have W1 at the forward end, W2 amidships and W3 in the after part. And of course, total weight will be sum total of all these three weights. Now we have buoyancy. In the forward part, we are now experiencing buoyancy B1. Now this buoyancy B1 may be same as the buoyancy which was earlier in the hogged condition. But here, when we say that between these two arrows, this arrow is broader, means the buoyancy contribution of the forward part is greater than the weight that is loaded in the forward part. So it's a relative representation between the weight and buoyancy in a particular section. So please read it only that way. So in the forward part now we have buoyancy which is greater than the weight, or weight is less than buoyancy, resulting into a net or a resultant upward force at the forward end. In the midship region, the buoyancy may still be the same. This B2 is same as the B2 earlier. Now, this B2 has fallen short of W2 because of higher concentration of the weights amidships. That means now in the midship region, W2 is greater than B2. Therefore, there is a resultant downward force in the midship region. In the after part, we have B3, which happens to be greater than W3 and resulting into a net or a resultant upward force at the after end. Needless to say again, the total buoyancy will be sum total of B1, B2 and B3. Now, if we again take the beam representing the vessel, now we have resultant upward force at the ends and we have resultant downward force amidships, which can be represented in this diagram here, and a downward force here. If you see this lower diagram, I'm sure you'll agree this will result in the beam bending in such a way that the ends move upwards and the midship part or the middle part moves downwards, and the beam is said to be then sagged, or the vessel is said to be sagged. If you can see in this condition, the green deformed condition of the beam or the vessel, now this is what is called as sagging. When sagged, the ship's midship draft shall be more than the mean draft. Why? Because the ends have moved upwards, the draft at the ends have reduced, so would be their mean. The midship region has bent downwards, so the midship draft has increased, so therefore the midship draft shall be more than the mean draft. During sag, the upper part of the hull would now experience compressive stresses. You can see in this diagram, upper part of the hull is the deck region and the one closer to the deck region, and you can see these portions experience compressive stress. Why? Because they are under compression. Likewise, the lower portions, that is the keel and the regions in the lower part, would experience tension and would be under tensile stress. Of course, there would be a neutral axis along which the length of the ship would remain unchanged. The length in the upper parts would tend to reduce because of the compression. Length in the lower parts will tend to increase because of tensile stresses or tension. Length along this so-called neutral axis would remain unchanged. So therefore again, like the hogging condition, even for sagging, the vessel has to be strong enough to withstand the stresses induced by compressive and tensile forces in the sagged condition. Having understood the stress set into the ship's hull because of the longitudinal deformation, now let us try and understand what is the effect of water outside the ship's hull on the immersed part. We know that part of the ship's hull is immersed. Why? Because it displaces water, which in turn creates the buoyancy. Now we also know that the pressure at any point below the surface of the liquid is equal to the depth of that point below the liquid surface multiplied by the density of the liquid multiplied by acceleration due to gravity. In case of ship structure, as the ship floats on the Earth's surface, G can be taken as to be practically constant. Why? because G is practically constant on the surface of the earth, barring a very small effect because of change in latitude, which can be ignored. So if we treat G as to be constant over the surface of the earth on which the ship is floating, so in ship stability, to keep the calculation simple, we say pressure is equal to depth into the density of the liquid, which implies that the pressure is directly proportional to depth of the point or the surface below the liquid surface. Now, if we consider the cross-sectional view of a ship as shown in the diagram, we have the waterline. We know that different points of the immersed part of the hull are at different depths, and obviously the pressure is directly dependent on the depth. So at keel, all the points in this cross-sectional view are at the same depth from the water level. So at all these points on the keel in the cross-sectional direction, the pressure would be same as shown by the same length of the arrows. So the length of the arrows in this diagram represent the magnitude of the pressure. Now, as the depth of the points will decrease as we come towards the surface of the earth, the pressure will keep reducing, and you can see the decreasing length of these arrows coming upwards. Now this pressure, which is acting inwards on the ship's hull, will tend to deform the ship's hull inwards, and you can see it will tend to deform the keel like this, deform the sides like this, more towards the lower part, lesser towards the upper part as the pressure is more as we go downwards. Whether the hull is eventually deformed or not, and to what extent deformed, will depend on the strengthening of the hull. But there is a pressure which is tending to deform, and this pressure which is tending to deform is setting stress into the hull. The magnitude of that hull will be directly dependent on pressure, so stresses will keep increasing as the depth of those points below the surface of the liquid keeps increasing. Similar situation is also experienced by all the boundaries of tanks carrying liquid inside the ship. Here we had the water outside the hull of the ship exerting this force inwards. If you have a tank which has its boundaries, bulkheads, sides, whatever, so if it carries liquids, it will also exert similar stress on all the boundaries of the tank, and obviously that will be acting outwards. The thrust on the boundaries shall be acting outwards. In this case, the thrust is acting inwards because the water is exerting the thrust from outside to inside, and this stress that is induced in the hull is said to be the stress induced because of the water pressure. Now we shall try and understand what happens if there is localized loading in the athwartship direction. We have already learned and understood the effect of non-uniform distribution of forces or loads along the ship's length, which cause the ship to longitudinally deform, resulting into hog or sag. Now, if the similar thing happens in the athwartship direction, that means there is a non-uniform loading in the athwartship direction, it shall also tend to cause the deformation in the athwartship direction. For example, if we load high density cargo, which is loaded very close to the center line and is not trimmed onto the side. For example, if you see in this diagram, we have a high density cargo loaded very close to the center line and not trimmed to the sides. So in this cross-sectional view, we can divide this cross-sectional view into three parts. One in the close to the center line and one on each of its sides. Now, as you can see in this cross-sectional view, if the buoyancy in all the three sections is assumed to be same, then I'm sure you'll agree that in this part, the weight will fall short of buoyancy. Why? Because the buoyancy would be corresponding to the complete weight. Weight out here is much lesser because the cargo is concentrated closer to the center line. So this part of the ship will experience a resultant upward force. You can see it here because of buoyancy being greater. Similarly, in this part also, we'll have a resultant upward force because of buoyancy being greater than the weight. Now, because of the cargo being concentrated closer to the center line, obviously in this part, we'll all agree that weight would be greater than buoyancy, resulting into a net downward force. What do we see in this ship in the cross-sectional direction? That on the sides we have a resultant upward force, and in the close to the center line we have a resultant downward force, which shall result into the deformation of the hull, somewhat like this, shown with this broken lines. Now, this tendency to deform the ship along these broken lines will set in stress into the ship, and this stress would be the stress induced because of the localized loading in the transverse direction. Now we will just discuss the stresses which are experienced by the ship when she goes to a dry dock. Now, if you are a new entrant to this profession, you may just skip this until you experience a ship being taken to a dry dock, or you learn about dry docking in a classroom scenario. Until then, you may just skip this and you could come back to this video once you have learned little bit about dry docking. For those who know about dry docking a bit, we can just compare it. It's a scenario which is reverse of what we just saw in the localized loading closer to the center line. In localized loading, just learned, the weight on board the ship was concentrated at center line compared to the buoyancy. When a ship goes to dry dock, she sits on the center line blocks, and the weight is primarily transferred to the center line blocks. As you can see in this diagram, this is the outer boundary of the dry dock, cross-sectional view of a dry dock in fact. Then we have this as the center line block. The ship, when the dock runs dry, the ship sits on the center line block. Now the weight of the ship is transferred to the center line block, and as per Newton's third law, the block exerts equal and opposite reaction or the upthrust. So what does the block do? The block will experience upthrust. We can divide the ship in the transverse direction in three portions the way we did in localized loading. Now along the center line here, the vessel experiences upthrust, which is equal to the total weight of the ship. Now what happens is, now there is no buoyancy. There is absolutely no buoyancy because the dry dock has been dried up and water has been pumped out. So what happens is, on each of these sides, on this side we only have the weight of the hull, this part of the hull, and there is nothing supporting it, so there will be a resultant downward force in this part. In the middle part close to the center line, this upthrust is equal to the total weight of the ship. Of course, there is no buoyancy, so therefore here the upthrust is much greater than the weight of this part, so there is a resultant upward force here. On this side, we only have the weight of this portion. There is nothing supporting it upwards, so there is a resultant downward force. Now in this cross-sectional view, if you see, closer to the center line, there is a resultant upward force. On the sides, there is a resultant downward force, which tends to cause a deformation as shown by these broken lines. This shows the tendency of the vessel to deform in dry dock. Like any other deformation, this deformation also leads to setting into the stresses. But of course, it's not during the normal service life of the ship. It happens only when the vessel goes to dry dock. Now we come to end of this video. We hope that this video will help you in better understanding of the stresses experienced by the ship's hull in static conditions. If you have any feedback, please do reach out to us through the comment section on the YouTube channel, or you may write to us on marinegurukul@gmail.com. Thank you very much for supporting us, for motivating us, and watching Marine Gurukul video series. Thank you very much.